All right, so correlation provides some useful information. Tells us if there's a strong positive or weak negative type of relationship, but it kind of leaves it at that. And often we're looking for more information. And really, decision makers are really wanting to understand more behind this relationship between X and Y, right? They like to ask the questions of, well, given I can increase X by so much, how is this going to impact Y? Or maybe I want to increase Y. Let's say Y is revenue. I want to increase our revenue to this level. What should I do with X to help make that happen, right? Or, we can say we have a weak, moderate, strong relationship, but what does that really mean? Like, is there actually a relationship that exists? So these are the kind of questions that we hope to be able to answer with machine learning, but we can't really do it with correlation. And this is where simple linear regression can actually help give us some of this information. And so simple linear regression is just going to build on top of correlation, but provide some added information that we can use, right? And we do this with what we call a best fit line, right? So if we go back to algebra, you probably remember the equation of a line, which is y equals a plus bx. And so the idea here is that we have y on our y coordinate, and our x coordinate is the x variable. And we have a here in this equation is our intercept. So basically when x equals 0, a equals some value. And then we have b times x, and b is the slope, so it's the rise over the run. At what is the rate of increasing of this line, right? And that's what b tells us, the slope. Well, we can use the same idea to fit a line to our relationship between our two variables, right? And so we can actually do this directly in R by adding this geom smooth. And so here we add this linear line that basically is modeling the relationship, the linear relationship between these two variables, right? Now, we actually call this a regression line. And behind the scenes, what this geom smooth is doing is it's actually computing linear regression or applying a linear regression model to get the necessary information to create this line. Now, when we do this, when we do simple linear regression, we move away from using this equation for the slope or the equation of a line, and we move towards this, where we have y equals beta naught plus beta 1 times x. And this is pretty much the exact same information, just written differently. Y hat, the reason we put this little hat on y is because it represents an estimated value, which is this blue line. Beta naught here is our intercept, right? So just like we had a in the previous, up here in this previous equation, we now use beta naught. And beta 1 is a coefficient that represents the slope. At what rate do we see an increase in this line? And so how do we actually get these values? Because, obviously behind the scenes, R has computed them and used them to create this slope. But how do we get them? Well, we actually get them when we fit our linear regression model. And we fit a linear regression model in the last lesson or the last module. But we really didn't talk about this model at all. But if we look at the model, which we can do with this tidy model, we get some output. We get our intercept, which is our beta naught. And then we get our estimated coefficient, which is right here, for beta 1, which is beta 1 is the coefficient for our x, which is the GR live area. So we can see we have our two estimated coefficients for our equation here. So beta naught equals 15,938, basically meaning when a home has no square footage or 0 square footage, the average expected sale price of a home would be $15,938. Does this seem reasonable? Not at all. Would we ever have a house that doesn't have any square footage? No. And we call this idea extrapolation. Extrapolation is when we're using values outside of the normal range of our predictor variable to compute a predicted value. All right. Now we have this beta 1 equals this 110 here. Right. So this is our slope of our line. And what this is actually suggesting is that for each 1 unit increase in our predictor variable, which is ground living area, for each 1 unit increase in that variable, our best fit line suggests that there is going to be 110 units increase in sale price. Okay, so for every additional square footage we add to a home, we expect there to be an added $110 to the expected sale price. That is our slope. This 110 is the slope of our model. So we can use this information and we could actually make predictions for a given house. So say we have house A here that has 3,608 square feet. This house actually sold for $475,000. But if we plug this 3608 into our equation, where we use our beta naught for our intercept, and we use 110 for our coefficient times the square footage, 3608, we get 411,618. So the predicted, this point on our prediction line, on our blue best fit line, is 411,618. All right, so we can see that the prediction is off from the actual value. It's actually off by 63,000. This is the error, right? The error is what our blue line predicts versus what the actual price is. And so we can see we are a little bit over $63,000 off. We also call this our residual. If we look at another house, right? So this home has 2,944 square feet. Our predicted value is 338,000, but the actual sale price is 150,000. So here, our blue line is far above or much higher, predicted a much higher value than the actual sale price. And so we have a residual or an error of about $189,000. That's how much it was off in that prediction. If we look at a third house, this one has 2,206 square feet. Our prediction on the blue line right here is $258,000, but the actual sale price was $300,000. So we see we have another error, an error for this home. The residual is $42,000 and change. So if we actually did this for every single home, we can see we have residuals for all of these homes, right? Compared to the actual predicted value that this line provides. So the way that we fit this line is we find the line that will actually minimize the square differences of all these residuals, right? So here is the actual metric we use to find our best fit line. And what we do is we take the actual sale price of our home minus the predicted or the blue line. We square that value for each house, and then we sum them all together, right? And so the line that actually minimizes this residual sum squares is the line that we use as our best fit line. All right, so you understand now how this idea of the best fit line can be used to kind of build on top of correlation to give us a simple linear regression estimate. And we talked about how we can get those coefficients that create the equation of our best fit line. And we saw that we have these estimates in our model output, right? Our estimate for the intercept and then the estimate for our predictor variable, which is equivalent to our slope. But when we look at our model output, we actually get a few other bits of information. So we get this standard error. So the standard error just represents the variability of our coefficient estimate. So just realize that, like many other statistics that we estimate, the coefficient is estimated with the idea that we're only seeing a sample of possible data, right? And so because of that, we tend to have some variability in the actual estimated value. So the standard error allows us to understand what is this variability that we have with our statistic estimate. Now, we also see this statistic, and this is for the t statistic. And within simple linear regression, the t statistic measures the number of standard deviations that our coefficient is away from 0. Okay, so if we were to take a look at our predictor variable here and the coefficient of 110, this is actually about 45 standard deviations away from 0. Right? We can use both the standard error and this t statistic, and we can use that information to calculate what we call the p-value. And lots of people are familiar with the p-value. P-value is typically measured relative to like a value of 0.05, right? So the p-value, so when I say that, lots of times what we say is the p-value less than or equal to 0.05. If so, lots of times we'll say it is statistically significant. Well, let's stay away from that interpretation, but let's just look at the actual value of the p-value. The closer that this p-value is to pretty much 0, then what we can say is that we're pretty darn confident that this estimated coefficient is statistically different than 0. So lots of times when we talk about the p-value, we do think about this in reference of 0.05, and that just means that we have 95% confidence that our coefficient is different than 0. Now, another way we can look at this is actually get the 95% confidence intervals of our coefficient. And we can do that by using this conf_int function. And when we do this, now we see that, all right, our coefficient estimate for the square footage area, predictor variable, is actually ranging from 104.9, so pretty much 105, to 114. All right, so this means that we can be 95% confident that the true coefficient is somewhere between this range, which we see that 0 is not in this range, right? So we can pretty much have very strong confidence that our coefficient estimate is statistically different than 0. Now, what you will find is when you have a predictor variable where there's a very low correlation or a very low relationship between that predictor variable and the response variable, then lots of times we'll see that the p-value may be closer to like 0.5. And then when that's the case, if we were to look at the confidence interval, we'd actually find that 0 would be somewhere in this range between this 2.5 and 97.5. And when that happens, then we can say that no, in fact, we cannot be certain or be very confident that that coefficient is statistically different than 0, which just means we don't have strong confidence that there's any type of relationship between those that predictor variable and the response variable. All right, so that is how we can use some of this additional information. Primarily what we look at is what is the coefficient estimate. That tells us the slope of our line. And then we can look at the p-value. And if this is extremely small, like it is here, very close to 0, then we have strong confidence that that coefficient is statistically significant and different than 0.